we'll discuss transformation matrix for a truss problem. This transformation matrix is very commonly used in ideal or course on advanced structural analysis, where you try to solve some problem using direct stiffness method. Here we'll see that why our transformation is required. So here we'll consider one simple problem, truss problem, and we'll try to justify why transformation is required. If you see that a truss problem is a problem where we can have axial deformations. So for this problem here, we have axial force act like this, and there will be some axial deformation. Okay, now if there is a member where axial force is acting and there is a deformation in the axial direction, we can correlate the force vector. Okay, you can write force vector like that way, that is equal to force vector and K matrix and is your displacement. Okay, so here if we consider 1 degree freedom at each node, 1 degree freedom at each node, in that case, we will have 2 by 2 matrix. Okay, so if you solve it, we will get our displacement which is acting in the axial direction. Okay, now if different member are inclined in different angle, okay, in that case, each member will have their force deformation relationship in the axial direction. For this case, it will be in this direction. For this vertical member, consider this vertical member, in this case, our force deformation will be related in this direction. If we consider another inclined member, we will have force deformation relationship along this direction. Okay, so each member will behave axially, it's fine, but they will behave along their axial direction. So if you want to assemble it and if you want to find the global stiffness matrix, in that case, we'll face problem to assemble it because each member is behaving in their own axial direction. Now, if you want to assemble it, in that case, what we do? We have to transform all the locally oriented member according to our global coordinate axis. Okay, and for that reason, we need that transformation. Okay, so before going to that, we'll see how we can write the stiffness matrix, how we can obtain the stiffness matrix for a simple truss problem, and then we'll proceed. So here you just see we've taken one simple truss, and this is your ith node, and this is your jth node, and we have applied Fi force at ith node such that it causes a deformation of unit amount. Okay, so if the deformation is causing deformations, or you can say if unit deformation is caused by a force, then we can say that is your stiffness. Okay, the force required for unit deformation is the stiffness. So here we can write force deformation required for unit deformation is your stiffness. Force required for unit deformation and is your stiffness. Okay, so here we can write that KII because we are obtaining unit deformation at ith node and also apply the load at ith node. So we can write that force F is equal to stiffness, that is your KII. Okay, so the same thing we can write here for axial member. We can write K in terms of AE by L into U1. Okay, how we are getting it? So you can see that U by L, it is your strain. If you multiply with that E value, then you will get that stress. And if you multiply with that area A, then you will get the force. So that way, basically, we can calculate. Okay, so we can write Fi. We can write Fi is equal to AE by L and your unit deformation. So that is basically K11. Here, if you see that this Fi force we applied here, and that also is causing the force as a reaction force, you can say, which is Fj. So amount of Fj will be the same as Fi, only the direction will be different. So we can write Fj that is equal to minus Fi in the opposite sense, and we have the same magnitude as above. And here we can correlate in that way that force developing at jth node due to unit deformation at ith. That is basically stiffness Kji. Okay. So we can write that Fj is equal to force developed at jth node due to invertible polarization at I, and that is equal to Ui. Okay. In that way we can write. Okay, so Ui is 1. So basically this is our stiffness. Now similarly, if we consider jth node, so again we can obtain Fj. Okay, and basically force required for unit deformations. So what we'll do, we'll apply that Fj force. So either there is unit deformation. Okay, so we can write basically in this way, Ae by L, that is equal to Uj, Ae by L into Uj, that value is equal to 1. So basically Kjj. Now again we can obtain that force developing at ith node. Okay, so here again this Fi will be same as Fj and opposite in magnitude. So Fi for this case will be minus Fj, and that magnitude is here Ae by L into U2, that's equal to 1. Now we can write as a K12 or K, or you can write Kij, very basically force required at, or you can say force developed, okay, develop at ith node due to unit deformation and at jth node. Okay, so you can write really Kij. Okay. Now here, if we combine all the four equation, here, equation 1, 2, 3, 4, we can obtain our force deformation relationship, that is very generalized form. Okay, that is in very generalized form. Here we don't know which node is fixed or constant, or how much force is acting there. So this is very generalized relations we have obtained. Okay. So here you can see this is your Fi is related here and Fi is related here. We are writing this thing here in the matrix form. Okay. And Fj, basically Fj is here and your Fj is here. We are writing in both the things in matrix form. Since we are considering very generalized form, we can write it in this way. Okay, so this is the basic thing we should know. Okay, basically how to obtain our force deformation relationship. Okay, for a simple truss problem. Here again, you just note at each node we have considered 1 degree freedom. Basically, we allow the member to deform in this direction only. So each node we have 1 degree freedom. So total node as here 2 nodes. So we will have a 2 by 2 matrix size. So this our stiffness matrix is coming as a 2 by 2 size. Okay. Now, thing is that if we consider 2 degree freedom at each node. Okay, so initially we have considered 1 degree freedom at each node and we have obtained this matrix. Each node we have 1 degree, here we have another degree, and you can obtain the matrix in that way. Okay, now if you consider 2 degree freedom at each node, 1 degree is corresponding to Ui, another is your along that Vi. Similarly here along Ui, Uj, here will be Vj. Okay, so we can have 4 by 4 matrix. Okay, so we can have 4 by 4 matrix and we can write the same problem. We can write that same problem. Okay, we initially obtain this matrix and we can write the same problem, same matrix. Okay, same this matrix in a 4 by 4 size, bigger size. Okay, so here you can see again we are obtaining the same value here Fui, that is equal to Kii into Ui minus Kij into Uj. The same thing also we can obtain here as a Ui as a Fi, that is equal to Ke, that is equal again K11 or Kii U1 minus Kij Uj. So same thing we are obtaining, only change we have done, that is we have write in a 4 by 4 size, since we have considered 2 degree freedom at each node. Okay, since in that along the v direction we don't have anything, only force we applied in the axial direction. So we have some value in the axial direction. Here we don't have any value, so that contribution here is 0. So K here it is 0, force is 0, here it's 0. Okay, here you just see we are writing Vi and Vj, but we don't know what are the values, so we are writing at a positive value Vi and Vj in some variable, but at the end it will be 0 value. Okay, because the member is oriented axially. and force was also applied axially. Obviously, along this direction there will be zero force. Okay, if we apply force along this direction, obviously this will try to deform in this direction. Here there will be zero force. So basically we are writing zero force, and since there will be V also will be zero. So if you multiply at the end, it will come as 0. But we are writing it in a generalized form. So we can write this 2 by 2 matrix into 4 by 4 in this way. Okay, now you consider if this thing is occurring for a member where our axial direction is along this. Okay, now if this member is oriented in some angle, if it's oriented in some angle, okay, and if you write in this way, okay, if you write in this way, so we can say this is our theta angle, and now our axial direction is your uj dash and vj dash if you consider jth node, and our basically at ith node our axial direction, the four deformation along the axial direction will be ui dash, and this side is which is perpendicular here, that is your vi dash. Okay, so our axial direction is changed from ui vi to u dash v dash. You can say our axial direction change from u v to ui to u dash v dash. Our axial direction now change from uv to u dash v dash. Okay, now if we consider this is our axial direction, then we can write this matrix in this form. There is nothing wrong with that. Here also it was axially oriented, uv, ui, vi, uj, vj, it was oriented axially. Here also ui dash, vi dash, uj dash, vj dash, that is also axially oriented. It is along this. Okay, it is also axially oriented, and axial direction is here. Axial direction is here along this, and this is your 90° here. This is also 90°. Okay, so now we can write this thing into this one. Now, if you summarize it, then we can see that our K matrix, okay, it is same. The same thing we are getting here. Only we're writing in a inclined coordinate systems, U dash and F dash. Okay, now our job would be to convert this inclined coordinate to our global coordinate systems, or other we can say we need to convert these local coordinate systems to our global coordinate systems. Okay, so our global coordinate system basically look like this. Our incline is like this. Incline is like this. Okay, our global is this one. Okay. Now what we'll do, we'll apply some transformation rule and we'll see how we can operate on that. Okay, so what we'll do, we'll write this U dash as a TU transformation matrix into U. Again, the force also will write as a transformation matrix to U. So here this is your vector, this is a vector. If you multiply these two, this also will be a vector. If you multiply these two, it also will be a vector. So we will not going to lose anything. Here also we are not losing anything from here to here. We are not losing anything. Here also we are writing U dash in terms of TU. Okay, now what we'll do, we'll do some mathematical simplification and we'll see. Okay, so now before going to that mathematical simplification part, let us see how our T matrix basically look like. Okay, so this part is very important. Here people used to have some confusions, but here we'll try to understand. Okay, so we try to spend some time here and see how basically transformation matrix look like. So what we'll do, we'll initially identify our U dash coordinate, U dash, okay, or you can say X dash, okay, and our V dash, okay, or you can say this X dash, or C to be our Y dash, and initially our X and Y. Okay, so otherwise you can say this is our dash coordinate and it is our along this our global coordinate. Okay, now here we just see this, we just considering one central line here and we're writing it here as a U dash, and this is our original UI and this is our VI, and this angle it is theta, so this angle also will be theta because if this need to maintain 90°, so this if this is theta, then this also will be theta because it need to maintain 90° there. Okay, so now here what we'll see, we'll see how much component is coming from here to here and how much component also is coming from here to here. Okay, and we'll try to summarize it. Okay, so here we just see u dash. You just see u dash is equal to u dash. Now we just see u dash that is equal to ui cos theta. So here from this part we'll have a component of ui cos theta. And here we have v, and initially this angle theta, this also theta. So from v we'll have a component of plus vi sin theta. Okay. So u dash is equal to ui cos theta plus sin theta. Now similarly we consider an obtain for dash. Here you just see initial angle between ui and vi was 90 degree. So it was 90 degree, and we have rotated of theta. So now we have u dash v dash. So angle between this one is 90 degree. Angle between u dash v dash is now 90 degree. So if this one also 90 degree. Okay, similarly this one also 90 degree. Okay. Now here we just see, if you try to see how much vi and ui is coming along the v dash direction. So here this angle is theta. Okay, so from here we'll get v cos theta. From vi we will get a component of v cos theta. Now here you just see from ui already we got that along u dash it is coming ui, along u dash we are getting component of, along u dash we are getting component of ui cos theta. Okay, now this angle is theta here, so this side will be ui sin theta. Okay. Now we obtain the value which is coming along v dash. We got the value v I cos theta. Here we got the value of y sin theta. Here on opposite side. Okay, so there will be some negative sign if we put it numerically here. So v dash that is equal to u y sin theta. So minus I am writing minus ui sin theta plus cos theta here. Okay. So I have written this part here, right hand side, so that I can put in this equation easily. Okay. Now, similarly, we can obtain for jth node also. You have obtained for ith node, we can obtain for jth node also. Okay. Similarly, we can obtain for jth node because this angle is same here. So it is I'm making the theta. Okay, and this angle along this and along this angle also 90 degree. Okay, so whatever the things is happening at ith node, same thing will happen at the jth node. Okay. Now again, we can write this thing in matrix form. So we can write u I dash v dash u j dash v j dash is equal to a matrix form into our u I v I u j v j. Now this is our basically transformation matrix. It's very easy to recall. You just see all diagonal term is coming as a cos theta. Cos theta, cos theta, cos theta, cos theta. Then off diagonal term here you can see sin theta minus sin theta. Here also sin theta minus sin theta. Okay, so it is very easy to recall. Now what we can do, we can write that our u dash, which is that our dispersion vector in the inclined or local coordinate system, that is equal to transposition matrix times our global coordinate axis. Okay. Now what we'll do, we'll do some mathematical simplification part. Okay, we'll do mathematical simplification. So what we'll do, initially we have obtained that our ku dash that is equal to f dash. Now what we'll do, we'll write ku dash means tu that is equal to f dash means tf. Okay, now what we'll do, we'll apply T transpose matrix in the both side. Apply T transpose on the both side. If we assume that T transpose is not a null vector, if that value or determinant of the T matrix is not 0, then we can multiply. Okay, so we'll apply T transpose K T U this side also T transpose TF. Okay, we can obtain this equation. Okay, so we'll see what actually look like. So here we can write in this way, and here we write T transpose KT, and here also will be T transpose TU. This must T and F. Okay, T transpose KTU, and here we'll get T transpose TF. Okay, now if you see this part will come as a identity matrix. If you multiply T transpose T, you will get identity matrix. So we can write that T transpose KTU, that is equal to F. Because the identity matrix I will come, so it is F we can write. And this part we can say our transform stiffness matrix K dash U is equal to F. Now here you can see what clever thing we have done. So cleverly we have changed our stiffness matrix so that we can have a force and deformation relationship in a global coordinate direction. Okay, so this is the thing we have done in the transformation. So we have transformed all the burden from U dash F dash to our stiffness matrix, and we obtain basically K dash U, particular force, where U is in our global direction, F also in our global direction. Okay, so here we have learned how we can get stiffness matrix, and then how we can get from 2 by 2 to 4 by 4, and then if we orient it, then how we can write this equation to in this form. And once we agree with that, we can apply some mathematical rule, some transformation rule. Okay, and transformation matrix, and we obtain transformation matrix, and we apply the transformation matrix here, and we transform our local coordinate systems to our global coordinate system. So initially we had U dash terms, from U dash now we are converted to U, and at the same time basically whatever the burden was coming in terms of our local orientation, that basically we have shifted to our stiffness matrix. Okay, and we obtain our relationship in the global direction. So I hope you get some idea. Thank you.